This sort of wraps up a few lessons in a row on vectors. And so we learned all different aspects about vectors, what they are, how to operate with them, unit vectors, zero vectors, separating horizontal and component forces of vectors. Now I'm going to introduce something called the dot product. And the dot product at the beginning is just going to seem like a set of calculations because it is. And then hopefully I'll give you some reasons why we might want to calculate the dot product. And if you take courses beyond this, you'll see the dot product show up from time to time, really anytime we work with vectors. So the dot product also has another name, is sometimes called the inner product. That's more of a linear algebra term for dot product. But in our case, we'll mostly just refer to it as the dot product. So the dot product of two vectors, first of all, has a notation that makes it look almost like a multiplication sign, but it's not. It's a dot, right? This thing over here is a dot. So it's the dot product of the two vectors. The way I calculate the dot product is by taking the first component of each of the vectors, multiplying them together, the second component of each of the vectors, multiplying them together, and then adding those two numbers. So I've got a number here, I got a number here. If I add a number and a number, I get a number. Also, sometimes we call it a scalar. In other words, the dot product of two vectors is not another vector. The dot product of two vectors is just a constant number, or scalar as we call it. What it does is it tells us a number of things, but one of the big things it tells us is information about the angle between the two vectors. So I put a little problem down the bottom. Let's find the dot product for those two vectors. We have no context for it yet, but let's run through the calculations. So if I call this u and I call this vector v, then if I take the dot product of vector u dot vector v, I'm going to take negative 2 times 2, right, the first component from each of the vectors, plus 5 times 3, the second component for each of the vectors. Negative 2 plus 2 is negative 4. 5 times 3 is 15. 15 minus 4 is 11. So we figured out the dot product is 11. Great. In a little bit, we'll figure out what we're going to do with that knowledge. So here's another couple of vectors. 7i minus 4j and 2i minus j. Find each of the following dot products. So it says find the dot products of v and w. All right. So v and w, I'm going to do in that order. So I'm going to do 7 times 2, right? First component times first component, plus negative 4 times, what's really over here is a 1. So negative 4 times negative 1. 7 times 2 is 14. Negative 4 times negative 1 is 4. 14 plus 4 is 18. All right, the second one says to do the dot product of w and v. So I guess I'll start with w this time and then work my way towards v. So I'm still going to do first component times first component, but I'll do 2 because that's the first component of w, times 7, that's the first component of v, plus negative 1, that's the second for the w, negative 4, that's the second for the v. So 2 times 7 is 14, negative 1 times negative 4 is positive 4, 14 plus 4 is 18. Oh, look at that. We get the same number. So it turns out the dot product is commutative. Why? Because all I'm doing is I'm switching the order that I multiply these numbers in, and multiplication is commutative. And so the dot product is also commutative. What if I take the dot product of w and w? So I'm saying I want to take the dot product of 2, negative 1, and then again 2, negative 1. All right, so I get 2 times 2 plus negative 1 times negative 1. 2 times 2 is 4. Negative 1 times negative 1 is 1. 4 plus 1 is 5. All right, you realize that this is the same thing as taking the square root of a squared plus b squared and then squaring it. So really I get a times a plus b times b, meaning that what I get when I multiply or I do a dot product of a vector on itself is I get the square of the length. If I want the length of it, take the square root. Interesting. So what am I going to do with this besides I just gave you an idea about finding length using dot product ideas? How about angle measures in between? Now, I'm not going to go through the whole proof that goes with this, but if you remember back to the law of cosines at the beginning of the chapter, we said that the third side is the sum of the other two sides squared minus 2 times side times the cosine of the angle between them, where this angle was included between two of the sides. And the value that was on the other side of the equal sign was opposite the given angle. Right? So opposite that cosine of theta is our u. So magnitude of u squared, because again, magnitude means length, so I need numbers, not actual vectors. U squared equals v squared plus w squared minus 2vw cosine theta. What we do is we do a process of solving essentially for the cosine of theta and then multiplying out. And what we end up with is this. As long as the two vectors are not 0, then the dot product is equal to the magnitude of the two vectors times the cosine of the angle between them. Oh, well now it seems like there's some use to that dot product formula. Because if I know the dot product of the two vectors, I can use that to find the cosine of the angle between them. You could reverse it the other direction and say that the angle is the inverse cosine of, I think of it as the dot products over the product of the magnitudes, right? So u dot v over magnitude u, magnitude v. You can stick with this original formula here. Dot product equals magnitude times cosine, and then just solve as needed. All right, let's give it a try. Let's try one. Vector A is 6, 4. So over 6, up 4. There's vector A. Vector B is 7, negative 2. Find the measure of the angle between them. So what do I need in order to do this? Well, the first thing is I need the magnitude of vector A. The magnitude of A is the square root of 6 squared plus 4 squared. So 6 squared is 36. 4 squared is 16. So add them together, I get 52. I'm not going to bother simplifying it because in a couple of minutes it's going to go into a calculator anyway. Magnitude of B, square root of 7 squared plus negative 2 squared. So I get the square root of 49 plus 4, square root of 53. The other thing I need to do the calculations is I need the dot product. So I need the dot product of those two vectors A and B. First component times first component, so 6 times 7, plus second times second, 4 times negative 2, gives me 42 minus 8, which is 34. All right, once we've done that, we can throw it all in the formula. I mean, you're welcome to do it sort of on the fly. I like setting up my pieces and then just throwing them in the formula. So the dot product, u dot v, equals magnitude u, magnitude v, cosine of the angle between them. So u dot v we said was 34, equals square root of 52, square root of 53, cosine of the angle between them. All right, let's divide both sides by the two square roots. And what that gives me is cosine of theta equals 34 over the product of the two radicals. And so then theta is the inverse cosine of this. You notice the square root of 52 and square root of 53 are each a little bit bigger than 7, right? Square root of 49 is 7, so this is a little bit bigger than 7. 7 times 7 is 49. 34 over 49 is less than 1. That's good, because either the cosine has to be 1 or less than 1. And so here, I'll get a valid answer. All right, let's throw that into our calculator and see what we get. Pause this for a second, do the calculations. I'll come up on the other side with an answer. All right, I came up with 49.64 degrees. All right, so it looks like this angle here is a little bit more than 45 degrees. That's the angle between those two vectors. And that's how we calculate it with the dot product. So we do the dot product over the magnitudes, and that gives us the cosine. So you could have jumped right away to inverse cosine of the dot product over the magnitudes and calculate it from there. I just wanted to show you that you can go back to that first formula and set it up that way too. All right, let's try this one. It says find the angle between these two vectors, round to the nearest tenth of a degree. All right, so the first one is 4 over 3 down. The other is 1 over 2 up. So the dot product, v dot w, is going to be 4 times 1 plus negative 3 times 2, which gives me 4 minus 6, which is negative 2. Is it possible for a dot product to be negative? Yes, it is. All right, let's find the magnitudes of each of those. Magnitude of vector v is going to be the square root of 4 squared plus negative 3 squared. 16 plus 9 gives me 25. Square root of 25 is 5. For w, I get the square root of 1 plus 4, which is square root of 5. So my formula says that the cosine of the angle is the dot product over the magnitude of the vectors. And so now take the inverse cosine of both sides, and let's see what we get for an angle measure. And then we're going to see if our original drawing was accurate or not. So I'll take the inverse cosine of negative 2 over 5 times the square root of 5. I get 100.30. So the way I drew it, it looks more like a right angle. One of them is actually pushed a little further in each direction, so it's an obtuse angle. That's how we end up with a negative cosine. Because remember, in the second quadrant, the cosines are negative. So it is possible to come up with a negative dot product. All that means is that when you come up with your angle measure is going to be more than 90 degrees. All right, what other types of information can we get out of dot products and vectors? Well, first of all, there is such a thing as a zero vector, and there are such things as 180 degree vectors, and they're vectors that are parallel to each other also. So if they're parallel, the angle between the vectors is either 0 or 180. If they're 0, they point in the same direction. So if I have a vector and then another vector, those vectors are parallel to each other because the angle between them is 0, meaning they point in the same direction. If the vectors are opposite directions, then the angle between them is 180 degrees. Interesting, but not as interesting as this. Ooh, a new big word. Two vectors are orthogonal when the angle between the vectors is 90 degrees. As you probably noticed from my definition in the pictures, you're probably more familiar with the word perpendicular. This is the symbol for perpendicular, like in my picture over there. Vector v is perpendicular to vector w. But you'll also see the word orthogonal. Orthogonal is just another word for perpendicular. The short version of why we use orthogonal is that these vector properties apply outside of dimensions that we can draw. And so we can draw things in 2 dimensions, right? We're doing it right now. You can draw things in 3 dimensions. You can physically construct something that has a 3rd dimension, in other words, a height. But these vectors apply to 4th dimensions and 5th dimensions and 6th dimensions, in which case there's no geometric property that matches with that. So instead of saying perpendicular, we say orthogonal. All right, so those words are kind of interchangeable in 2 and 3 dimensions. Outside of that, we tend to use orthogonal. That's the short version of why we have another word for perpendicular. Why not just say perpendicular? Well, the cosine of an angle that's 90 degrees is 0. So remember we have that formula that says the dot product equals the magnitudes times the cosine of the angle between them. Well, what if theta is 90 degrees, or pi over 2? Then this thing over here is 0, which means that that thing over there must be 0. So if the dot product is 0, the vectors are perpendicular. So if the dot product is 0, then the 2 vectors are perpendicular or orthogonal to each other. Which means sometimes the question might simply say, are these 2 vectors orthogonal? In which case you calculate the dot product, and that gives you the answer. All right, so are these 2 vectors orthogonal? I like writing my vectors like this. 2, 3, and 6, negative 4. So I calculate the dot product. U dot v equals 2 times 6 plus 3 times negative 4. 2 times 6 is 12. 3 times negative 4 is negative 12. The dot product of those 2 vectors is 0. So yes, they are orthogonal. What do they look like? Over 2 and up 3. Over 6 and down 4. Right? So those two vectors have a right angle in there. How did I know that? I mean, besides drawing it, I can't draw it that accurately, so I can calculate the dot product. If the dot product is 0, those two vectors are perpendicular. So that's one of the uses of the dot product, not only to find angles between two vectors, but there's a shortcut for what happens if we want to find out if the angle is 90 degrees between the two vectors. Dot product is 0, vectors are orthogonal, or as we might get used to calling them, perpendicular.